All right. Differential equation is what we want to look at, which is called differential calculus at this level. So by the end of this, we should be able to explain the concept of derivative, differentiate explicit function, differentiate implicit function, and what have you. First of all, limit value of a function. Now consider the function f of s equals to s squared. What value does the function take at s equals to 2.1, 2.01, and etc? The value of f of s at the given value of s can be summarized in this table. So what to do is that each of these value, if you put it in the place of s of x, square each of these value to give you all of this in this table. You will observe that the sequence of numbers, this down to 1 all over 10 all over 10 raised to power n, get closer and closer to 2. Yes, if you look at the value in the table, we get closer to 2 approximately. And so if that is the case, as the sequence of the number 4.41, this and this etc get closer to 4. So if you continue to square this number, all these values, they will get closer to 4. All right, so consider again the function f of s equals to s squared at the following values of x. Look at these following values of x. So if you look at the table, you discover that f of s will give us all of this, you see. So if you look at that value very well, they are, again, there is an observation that they are turning to approximate value of also 4. You can approximate this to become 4. All right, so this is what limit is trying to tell us. So we say that the limiting value of f of s equals to s squared as s approaches to either from the right or from the left is 4. Okay, so to differentiate between the statement the limiting value of f of s as s approaches to from the right, and the statement the limiting value of f of s as s get closer and closer to 2 from the left, will introduce a notion. Look at it here. That means lim of f of s as s tends to 2, that is positive, equals to 4, is the notion for limiting values of f of s as s approaches 2 from the right. So what it means from the right is that as x turn to 2, and that 2 is indicated by the positive, look at it there, positive sign, so that is from the right. Okay, it is called right hand limit of f of s as s tends to 2. So we call it the right hand limit. So lim f of s equals to 4. Look at the sign now, as s turns to 2, and the negative sign is a notation for limiting value of f of s as s approaches 2 from the left. It is also called the left hand limit of f of s as s turns to 2. Okay, so this is all you need to do. So the approaching values as s turns to a particular figure, it could be from the right or from the left, and that can be separated by negative and positive. Now we have properties of limit. We state without proof the following properties of limit. So these are the properties of limit. So at this level, well, there will not be proof. So if you want proof, you go and look for more of my higher for universities, the differentiation calculus for university level. Okay, so now first of all, the limit of k is equals to k, that is as s turns to a constant, which is a. The limit of a constant is the constant itself. That is what it means. All right, so now the lim of all of f of x, f of 1s, f of 2s, down to f of ns will be equals to the limit of f of 1s plus f of plus the limit of f of 2s down to f of ns. Now what it means is that if you have a limit of sum of functions, you can actually, the limit can be distributed over each one of them. You can introduce the limit to each of these functions. That is what we have here. All right. Okay, so that is just the explanation of it. The third properties is that the ln as s turns to a of this function f of f1 of s minus f2 of s is equals to the lim of f1 x minus lim of f2 of s. So it also holds for subtraction. That means here multiplication can distribute over subtraction, as it can also distribute over addition here. So the next one is the limit of f of 1 of an f of 1 x, f of 2s multiplied down to f of n x. If you have this limit can be limit of f of 1 s dot limit of f of 2s down to limit of f of n x. Okay, so what it means is that even the lim can be distributed over multiplication too. Okay, so that is the limit of the product of a finite number of a function is equal to the product of their respective limits, like as I've explained before. Okay, so the property continues. So number 5 property. Now let's look at for addition. Does it work? Lim as s turns to a or constant of a function divided by another function, it can also be distributed over division. So you see that the lim of the numerator take the lim, and the denominator also take the lim. Okay, so now we say provided that the function that is occupying the denominator is not equals to 0, because if f of 2 of s f2 of s if is equals to 0 now, so you discover that all of this lim will become returns to nothing. Then the next property, lim of a constant multiplied by f of s is also the same thing as k lim of lim of that f of s. So if you have a constant with a function multiplying a function, the lim of them together, the constant can go to the back of the lim, while the lim take effect on the f of s on the function of this variable s. Now we have an example. Now evaluate lim as s turns to 0 of this particular expression. So now to do that, it discovered that solution, our lim as s turns to 0 of this function will be equals to the lim of 7. You are going to distribute the lim by each of the term, and which satisfy one of the properties that lim can be distributed over subtraction, so an addition. So this is what we have here. So lim of a constant, of course, is a constant from one of the property. Lim of a constant is always a constant. So you see, this is 2x, and according to one of the properties, 2 is a constant and it can move behind a lim. So we are going to have minus 2 lim of x. So this x remain. So it is the same thing as having lim 2s, which would definitely the 2, which is a constant, will go to behind the lim. So the same thing happened here too. 5 come behind the lim, while the variable x squared remain. Also here too, 4, which is constant, come behind the lim, and the variable s raised to power 3 remains. So as s turns to 0, you discover that this x will become 0, here will become 0, here will become 0, and of course a lim of a constant, which is 0 now, is still 0. So 2 times that 0 will give us this 0. 5 times 0 here will give us 0. 4 times 0 here will give us this 0. So, and then lim of a constant is the same as that constant, which is 7, and that is what we brought down here. So 7 minus 0 plus 0 minus 0 is equals to 7. We have example 2 here. This example 2, you can see that it is division. Lim as s turns to 0 of all of this, the lim can be distributed over each one of them. Now let's do it together. Look at it. So the lim of all of this expression is the same thing as the lim of all the numerator all over the lim of the denominator. So you discover that you can distribute the lim for each of the 10. You have lim given to s square, given to 5s, given to 9, and that is what we have here. And of course, all of them, the s is turning into 0. Also, we have it here too. Look at the lim here. The lim for each of the 10 is distributed over each of the 10. Then from there, as x turns to 0, here of course will become 0, and then x will become 0. Lim of a constant is the same as that constant, so lim of 9 is 9. So all the two turns, this one turns to 0, 0, and the 9 remains. So here, because x is here, s turns to 0, s is here, s turns to 0. Anything multiplied by 0 here is 0. So here, lim of a constant, which is 15, is 15. So 0 reacting with 9 is still 9, and also 0 reacting with 15 is still 15. So 9 all over 15 will give us 3 over 5. Okay, so look at another example here. So this example is similar to what we did before, only that you just need a little expansion here. This is a quadratic equation which you can also always expand. So if you have something like this, as s turn to 5, there are two ways you can do this. You can either go direct, directly by substitution, or you can expand actually. So expansion will be more easy. So you discover that if you expand s squared minus 25, it will give us s plus 5 and s minus 5. All right, so this is what we call this expansion of this. So all over we have s minus 5. The essence is just to cancel out x minus 5 will cancel out s minus 5. We are left with s plus 5, and this is what we have here. So if that is the case, then the lim as s turns to 5 will become lim multiplied by lim over s, and then the lim also will be distributed over 5. So if that is the case, you are going to have, as s turns to 5, here will become lim 5, and then lim 5 still remains. So lim 5, it will become constant. Lim of 5 is still the same thing as 5. The lim of 5 here is still the same thing as 5. So 5 plus 5 is equals to 10. So look at this example again. You can pause the video, check if you can actually do direct substitution to see if you can get the same answer, which I doubt. Okay, so now we have more examples that you can actually look at. You have something like this. I'm not going to explain this again. I'm going to play the video softly. You can see it now. You can pause the video and check the steps. Check the steps. You can check the steps that I use. Look at it. You can pause the video to look at what is done. All right, I just want you to think deep. It's something you can do. Okay, you can do it actually. All right, thank you. So continuity of a function. A continuity of a function. A function g of s is said to be continuous as at s equals to b if and only if the following conditions are satisfied. So when we say a function is continuous, all right, so now let's look at the properties or the condition that can make a function to be continuous. So if f of g of s is defined at s equals to b, that is if g of b exists. There are some functions that if you substitute the variables into, they don't exist. They turns to infinity. So if it does not exist at all, then if it does exist rather, then that is the first condition satisfied. Then for a function to be continuous, the lim of this function of this variable s have to also exist. So the function f of g of s has to exist. The lim of it also has to exist as x turns to b. Okay, so now let's look at it very well. The third, look at my cursor. The third property is that, or condition, the lim of g of s equals to g is equals to g of b. That is the limit as s turns to b of the function g of s as s approaches b is equal to the value of the function g of s as at s equals to b. So at s equals to b, if this x can be equals to this b, at any point you pick the value of s to be equals to the value of b, then the limit of g of s have to be equals to the value of the function which is g of b. That is what that properties is talking about. Okay, so the condition rather. So now the properties of continuous function, let's look at the properties. Now what we just saw now is a condition, that is for a function to be continuous. So now let's look at the properties. How does it behave? We state without proof the following properties of continuous function. So every constant function is a continuous function. So if a function is constant, then that function is definitely continuous. So every polynomial function is a continuous function. So if any function has a power, its variables has a power more than 2 upward, 3 4 5, yes, from 3 upward, you discover that that function is going to be continuous. Every rational function is a continuous function. Okay, any function that is rational is a continuous function. So if f of g and h of s, g of s rather, and h of x are both continuous at the point s is equals to b, then g of s plus h of s is also continuous at point x is equals to b. Okay, so now this x here is a mistake. It is actually b, h of b. So take note of that. So h of b. All right, so if the variables are equal to themselves, all right, if the variables are equal to themselves, their functions, at the addition of their function, is also continuous at the point where they were equal to themselves. All right, the next property is that if g of s and h of s are both continuous at the point s equals to b, then g of s dot and h of and b is, remember I told you this is b, is also continuous at the point s is equals to b. Now if c is a real constant number and g of s is continuous at s equals to b, then c g of s is also continuous at s equals to b. So that is a constant be multiplied by a function. Also, if g of s and h of s are both continuous at s equals to b, then g of s and then divided by h of b is continuous at x equals to b. So this is also true for division if and only if the denominator, which is h of b, is not equals to 0. Now if g of s is continuous at s equals to b and g of b is not equals to 0, then 1 all over g of s is also continuous at s equals to b. So that is a reciprocal of it. The reciprocal is also continuous. So these are properties that you can actually become familiar with as you go over them again and again. If g of s is continuous at s equals to b, then g of absolute value of g of s is also continuous at s equals to b. So if the function is continuous, its absolute value will definitely be continuous. All right, so note a function g of s which is not continuous at a point s equals to b is said to be discontinuous at the point s equals to b. So if any function is not continuous at all at when the variables is equals to a specific value, then that function is called discontinuous function. The point s equals to b is called a point of discontinuity if at all the function is not continuous of the function g of s. Also, if a function is discontinuous at an interval, then it is also said to be discontinuous in that interval. All right, so that is all about the properties. Now we have an example. Look at an example here. Examine g of x equals to all of this expression for continuity at s equals to 2. So at s equals to 2, is this function g of s or equals to all of these things, is it continuous or discontinuous? Let's see, let's check. Okay, so we substitute g of s is this. So g of, when s is now 2, you substitute 2 for s in any point you see it. So by the time you check, you do this calculation, you discover that you're going to arrive at 47. So by the time you arrive at 47, thus g of s is defined at s equals to 2. So that's one of the properties, that g of s exists. Okay, so and it exists because we have the value. It is something that has value 47. So at 2, the function actually exists. So let's check whether the lim of it also exists. The lim of this function, if you distribute this lim over each of these 10, which is what we have here, so as s turn into 2, you discover that we are going to have lim of what? Of 8, because 2 raised to power 3 here is 8. Lim of 8 is still 8. Lim of a constant is constant. So this 4, which is a constant before, move behind the lim, and that is what we have here. Of course, I've explained it earlier. And 4 times the same thing happened here, and let's say the same thing happened here, the same thing happened here. 4 times 8 will give us 32. Also, if you multiply all through this, you have these steps. This times this plus this plus this plus 4 minus 1 will give us 47. So also you discover that the limit of the function, the limit of this function also exists. Okay, so the limit of g of s is equals to the function g of 2, which is the same thing as 47. So both their limit and the function is the same. Hence g of s is continuous at s equals to 2. So this is how to check the continuity and discontinuity function. Now the gradient function properly. Now remember, we are looking at differential calculus. Gonna consider the curve whose equation is given y is equals to f of s. So there is going to be a straight line graph, and together with a kind of a curve. So you have your tangent drawn to it. I will take time to explain this, of course, from our elementary graph. Now our m will be the gradient. Okay, if m is the gradient, so gradient is always you could call it gradient or slope. It is actually increase in y all over increase in s. Okay, so from our previous coordinate geometry, you discover that our m is equals to increase in y is the same thing as y2 minus y1 all over s2 minus s1. So suppose that s2 minus s1 is equals to change in s, and at s not equals to 0, since s1 is not equals to s2. Had it been s1 is equals to s2, this minus this will be 0. Since they are not equal, s2 is not equals to s1. So therefore we discover that our s2 is going to be equals to s1 plus delta change in s from this simple expression. If our, of course, what it means, s2 minus s1, what it means is that it means change in s. So if it is change in s coordinates, so you discover that this is delta s, which means change in s, which is, so if you make your s2 the subject of formula, you are going to get s1 plus delta s. So therefore y1 will be equals to f of s1. All right, f of s1. So y1 will be f of s1, because that is where we got our graph from. Remember, we said this graph, the whole of this graph is actually y equals to f of s. Okay, so if that is the case, you discover that for y1 we have f of s1, for y2 we have f of s2, which is going to be equals to f of s1 plus delta x. Why? Because s2, we say let our s2 here, we define our s2 here to be equals to s1 plus delta s. So if that is the case, you discover that f of s2 is the same thing as f of s1 plus delta s, because that's the value of s2. So therefore, if you look at this particular expression, our slope now will be equals to, which is equals to y1 minus y2 minus y1 over s2 minus s1 will be equals to our y2 is given to be f of 1, which is this f of s1 rather, f of s1, which is we have it as f of our y2 is f of s1 here, then our y1 rather is f of s1 here, then our y2 is given to be f of s1 plus delta s, which we will have here. So all of this is y2, all of this is y1, so all over s2 minus s1 is now our delta s, because we have defined it here. We say suppose we put s2 minus s1 to be equals to delta s, and that is what we have here. So if we can get something like this, now what does it really mean? Okay, what does it really mean? So let me not, you can pause the video to read this, but let me just start explaining from here. If delta s is made to approach 0, the function m of s, because it approaches 0 now, we have m of s is going to be this value. It is now called the gradient function of y equals to f of s. So this is what we call the gradient function. All of this we derive now is called gradient function. Why is it not gradient function? Because the change in s is now made to approach 0. It is approaching the origin. All right, that is what it means. If you look at the graph, you discover that it approaches this origin. So because of that, that is what we are going to have. Okay, this is going to help us in our, as we continue with this, this lesson. The derivative of a function, so the changes, okay, the changes that occur. If you look at this is a graph where we have a little modification here. You discover that at this point we have f of s. Here it changes to s plus delta s. Here you discover that f of s plus delta s is now taken from f of s. So this is a little modification. All right, so in this case we recall before now that our y is equals to f of s, which from it we are able to get this gradient. Now that we have gotten the gradient, at all of this I will be explaining it why I so we say that m2 is a limiting value of m1 as data turns to 0. So if we take this data to turn to 0 now, we introduce lim. Okay, so and the whole of this thing will become our f of 2 because we introduce our lim, and introducing this lim this time around, this data is now approaching 0. The change is approaching 0, and it is denoted simply as f prime of s. That is the first derivative of s. Thus f prime of s is called the derivative of f of s. Okay, and this can only happen when the gradient, the gradient is, you introduce limit to the gradient at the change in s move towards or tends towards 0. Okay, so that is what derivative mean. A limiting value of a gradient at the changes that is occurring at the s axis is approaching 0. Okay, so now let us consider again the function y equals to f of s. A small increment in s will cause a small increment in y. That is what it means. So if we represent the small increment in s by delta s, then we can also represent the small increment in y by delta y. Thus if y is equals to f of s, then the small increment by this x, which is delta s, will also lead to small increment by s, because this y actually is what we call dependent variables. It depends on s, this function of s, to exist. So if anything, if s become pregnant, that what it means is that y will also become pregnant. Okay, so now this is just the graph to illustrate that. Okay, if anything, this is actually change in s, and this is change in y. All right, okay, so this is change in y. So if anything, if there's any little increment, by s, it will take value on the y too. So that is what it means. Look at the increment on s, and this is the increment on y. So it is very, very important you understand these graphs. So if you understand it like this, it will not be a difficult thing for you to excel or to succeed in this particular topic. So if m1 is the gradient of the secant AB and m2 is the gradient of the tangent A, you see m2 is the limiting value of m1 as delta x turns to 0. So I've explained all of this from my statement. So we can call this expression ds dy ds, which is dy ds. That is what it is called. Okay, so now look at it here. So we can represent that dy ds as f prime of s, which is read as f prime of s, or differentiation of s, which is read as dds of s, or you can also read it as df by ds. So if y is equals to f of s, then dy ds is equals to f prime of s. Okay, so these things are some of the things we call them notation. So the notation dy ds and f prime of s will often be used interchangeably. Sometimes dy ds is called the differential coefficient of y with respect to s. So as we proceed, the different meaning associated with dy ds will be unfolded. Okay, but for now, let's continue with what we have known. All right. Okay, so this introduction is very, very important. The y ds is either the gradient of a function of a curve y equals to f of s, or the rate of change of y with respect to s. So that is what it means, the grand meaning of it. Differentiating from first principles. So how do you use the first principle to differentiate a function? So let me go to the example straight. Find the derivative of f of s equals to s squared. This is a function now. Okay, use the first principle to find the derivative of this. The first principle is based on all of this thing I have explained. If you don't understand it, you can play the video again. So it's just like a graphing system, and the behavior here is just actually as the right hand side increase, the left hand side increase. So with mathematical, as the independent variable increase, the dependent variables also increase. That's what it means. All right, so now if f of s, which is a function, is defined to be s squared, so you discover that as you increase x by delta s, as the little change occur here, the little change also occur with this function, too, f of s. So it will now be f of s plus delta, and then because there is square here, the square will be introduced. If you expand this quadratically, you discover that it will give us s squared plus 2s delta s plus delta s all square. All right, so if this is the case, you can actually see here that our f of s, f into bracket of s plus delta s minus f of s will be equals to delta because of s plus delta s all square minus s square. Now what actually happened here, you are subtracting f of s from both sides. That is what you do, subtracting f of s from both sides. So f of s minus all of this minus f of s, and then here the f of s is already defined as s squared. So if you introduce it here, you discover that it is the same thing. This expansion is, we have found it before, is what gave us this, and therefore minus this x, the x here, we cancel this s square will cancel s square, so you have 2s delta s plus delta s all square. That's what you have, and all of them will be equals to f of s plus delta s then minus f of s. That is what you have. So if you divide both sides by the coefficient by delta x, delta s will cancel delta s here, then delta s will cancel one of the delta s here. You are left with only 2s here, then you are left with one delta s here. So divide, as you are dividing through by delta s, it will reflect on this left hand side. Look at it here. So now if you have this now as delta s turned to 0, remember we say for a differential coefficient to be found, the delta s must turn to 0, as you have established before. As delta s turns to 0, you discover that this delta s here will become 0, so you are left with only 2s, and that's what we have here. So if it turns to 0, you discover that here this particular place will also become 0, so s plus 0 is 0, so f of 0 is still 0. All right, f of 0 is still 0. So yeah, and if that is the case, you discover that what you'll be left with is actually f of s, and this f of s, since it has turned to 0, is going to form a f prime of s, which is the differentiation, and the value remains 2s. Okay, so find the derivative of y equals to s raised to power 3 from the first principle. The same thing holds here. Okay, so y is equals to x raised to power 3. Increase the right hand side and increase the left hand side with delta y and with what? Delta s. So all of them is enclosed raised to power, in bracket, raised to power 3, because the 3 is there. So this is what we have. So by the time you have this, if you expand this, if you expand it, it's going to give you this. Remember your polynomial expansion. If you do polynomial expansion here, it's going to give you this. So if you have not learned polynomial expansion by now, you should have have a little glee of it. Okay, so what you have here is that y plus delta s is equals to all of this. So you can take y to the other side, to the right hand side, change to minus y. That is what we have here. To change to minus y. So we are left with our delta y here, so which is equals to the what we have initially, s plus delta s, and then minus s raised to power 3. So you are going to have all of this. If you expand this, you have this. Okay, so that is what it means. By the time you've done that, this is a value of y which we actually subtracted. Here is supposed to be minus y, but the value of y from the start is actually s raised to power 3. So if you say minus s raised to power 3 here, the minus s raised to power 3 will cancel this minus s raised to power 3, and that is why we are left with this expression now. Here the s raised to power 3, which is here before, has gone. It has been cancelled by the value of y, which we take from here to the right hand side. So therefore, if you have this, divide both sides, divide through by the change in s, which is delta s. So if you divide through the delta s, we cancel delta s here. You are left with 3s squared. Here delta s will cancel one of these. You are left with 3s delta s. Then delta s will sorry about that. Also delta s we also cancel from here. You are left with 2 of them now. So as delta s turns to 0, you discover that delta y over delta s will become dy ds, and then here will become 0. 3s times 0 is 0. Here all of here will be 0. You are left with 3s squared, and this is 3s squared we have. Hence the dy ds will be 3s squared. Now find the derivative of 1 over s from the first principle. So I'm going to play the video slowly. You can look at it now. Just look at it. It's the same principle, the same principle. Y is equals to 1 over s. Okay, so the next step is increase left hand side and the right hand side with delta y and delta s. So you see 1 over s is increased by 1 over s plus delta s, and then y plus delta y. You see y is increased by delta y. So if that is the case, you are going to have take this y to the right hand side, change to minus y. So the value of y before is 1 over s. So that is why we have 1 over s plus delta s minus 1 over s. Now you're going to do a little algebraic activity here. The LCM between of s plus delta s and s is the same thing as s plus delta s, all in brackets with x. Alright, so if you have this, the denominator here divided by this denominator, this x plus delta s will cancel it. You are left with only s. S times 1 is x. Then if all of this, the denominator here divided by this denominator, s will cancel s. You are left with s plus x multiplied by 1 is what we have here, minus s plus delta s. So our delta y will be equals to, if you open this bracket, minus times s is minus s, minus times plus delta s is minus delta s. So all over s, if you open this, if you repeat the denominator again, that's what we have. Of course, x minus s is 0, so you are left with minus delta s, and that is what we have here. So if that is the case, divide through by delta s. If you divide through by delta s, you are going to have delta y over delta s, still the same as minus delta s all over s into bracket of s plus delta s or bracket divide by the delta s you have here initially. So this delta s will cancel this delta s up there, so you are left with minus 1 over this. So as delta s turn to 0, our our delta y all over delta s will be equals to, because here will become 0, s times this s will be s square. So the minus here is what to reflect here. So 1 over s square is what we have. Okay, so look at what we have here. So our hence our dy ds will be minus 1 over s square. Alright, find the derivative of y equals to c. The c is a constant. So of course derivative of a constant is a constant. So look at it step by step. You can look at it now. You can pause the video and look at it. I'm scrolling through. Okay, so hence the derivative of a constant is 0. Rather, derivative of a constant is 0. Find the derivative. Find from the first principle the derivative of y equals to as plus b. A and b are constant. Okay, so if you can look at it, apply the first principle which you know already, you discover that the y ds is going to be a. So what is the conclusion from here? The derivative of y equals to x raised to the power of n. So if you have this, let's have sorry about that. Okay, let's go. So therefore dy ds is equals to a. So now the derivative of y equals to s raised to the power n. If you find this derivative, look at it very well, which is, I don't want to explain this, bore you with this explanation. All is taking us to a particular formula that we can use to find derivative. So you discover that your dy ds will be ns raised to the power n minus 1 if y is equals to s raised to the power n. So anytime you are doing derivative, you use the power to multiply the coefficient of the variable s and then reduce the power by 1. That is what it means. So the relation is true for integral and functional value of n. So now it makes differentiation simple for us now. So find the derivative of each of the following, no longer using the first principle. So you can go straight to find this. So the first one, y is equals to s raised to the power 7. So dy ds of this value is going to be 7x raised to the power 6. Why? Because anytime you're finding a derivative use the power to multiply by the coefficient of the variable, and the coefficient of the variable here is 1. So 7 times 1 is 7. Reduce the power by 1. If you reduce 7 by 1, you are left with 6. So the derivative, which we call dy ds, is going to be 7 or 7s raised to power 6. Also, it goes for others. Y equals to 1 over s squared. You know, we have used first principle to solve this problem before. So this is the same thing as the coefficient here, the power here rather, is half. Half times the coefficient of this variable is 1. So half times 1 is 1 over 2. And then reduce half by 1 is going to be minus half. And then we have half s raised to power minus half, which is the same thing as 1 all over 2 root x. Why is it root s? Because of this square root, which is all over the power, which is 2 here. Okay, so the next one is y equals to 1 over s raised to power 3. So if you run down through it, you discover that, look at it, the process is the same. Y equals to cube root of this, all of this thing can be written as s raised to power 2 over 3. So s raised to power 2 over 3, you can differentiate. Use this power multiplied by the coefficient of this, which is the same thing as 2 all over 3. Reduce the power 2 over 3 by 1, which will give you this. So from there, 2 over 3 whole stands, and then this 3 all over the power raised to power of